Welcome back. I'm checking our stream, making sure that we're ready. We have an excellent connection. It's loading. Excellent connection. Sounds loading. Excellent connection. Cool. All right, so change this to winter 25. Just keeping track of some of the work as I go through this. I end up doing this doing the project multiple times and looking at all sorts of different answers. So in the last video from yesterday, I was looking at how do we define this this value of k using a finite difference method. One thing that I saw that was interesting was someone took this formula, so this exact formula, and compared it to this differential equation. So this is an exact differential equation. This is an exact solution to that differential equation. So thinking about what is k if you know, so if we have this value, spectacle, rectangular, oh, I already got it. So we'll copy that, bring it over here, discard all this, paste it in. So I know this is I just want to make it a little smaller so it's not so pixely. I know that this is, so if I say t of 45 minute is 80 degrees, so 80 equals TA, so 65, where this is 65 degrees. This one is 85 degrees. This one is 65 degrees, equals that plus 85 minus 65 e to the negative k of 45 minute. So I could plug in a value here and get a little bit of a better approximation for that value of k. So then I have 80 minus 65 over 85 minus 65 equals e to the negative k, and I'm going to write it as 0.75 hours, like that. Then the log of 15 over 20 equals negative 3 over 4 times k, or k equals negative 4/3 times a log of 15 over 20, something like that. So let's see where that brings us. So I got that k was 1/3. I'm online. So k was 1/3 in this case. Let's see what log of 15 over 20 times 4 over 3 is 0.384. And then I could also compare this to, here, we'll copy that, paste it down below, and say and remember this was or not remember, okay, yeah, forget about that. You don't have to remember everything from previous videos. But when I say that the current temperature, when I define a derivative based on two different temperatures, there's one slope to define them. But the question is, where is that slope being defined? Is it at the current time of 11 a.m. or is it at the current time of 11:45 a.m.? At 11 a.m., that would be this 80 degrees, or sorry, that would be this 85 degrees. This is a forward difference method where I'm using the next temperature to define what the derivative is. If I say the current time is 11:45, that's a backward difference method where I say this slope is the slope at 11:45 a.m., not 11 a.m. Both of them, and we can see that both of them are a little bit wrong. So this is my K forward, this is my K backward. This is kind of my, yeah, we'll plug this in. It's like a, and we could try this, KF, KB. If I look at the average of my forward and backward methods, I end up getting pretty close to this log of 15/20 times 4/3 and 0.388. So whatever value of K you want to use is okay for this assignment, but you just got to choose something. Like I'm using a forward difference, I'm using a backward difference. If you're plugging in this equation, like that means that you're solving this differential equation and then trying to figure out what that value of K is here. So somehow keeping track of your work, some comments, some demonstrations, like what's going on, where are these values coming from? And like if you're getting ChatGPT to help you out, or any kind of generative AI, if you're using ChatGPT or Google, like Copilot or any of those, and it's helping you form how you're approaching this project, then think about like where are these results coming from? Like why use why use a forward versus a backward versus an average of the two, something like that. And most people did a pretty good job creating functions, and it seems like there's a lot of work trying to like turn this work into functions. And so what I saw was like in here, I made whenever you just have like a for loop with things being calculated and stuff is getting stored in the computer this way, these are usually just called scripts. They're just kind of, you can edit the script and rerun it, but it's not like a reusable kind of piece of code. I saw a lot of people kind of turning this into a function. So taking this and saying define like Euler temps of, and I don't know what I want to use yet for function values. I'm just trying to, there we go. So I'll say like n is one of my inputs, T ambient, we'll call that 65 degrees. I like to plug in default values if I'm gonna define functions like this. T0, and if I'm defining and T final, and so this is kind of what I saw, is that people were taking this this set of work and turning it into a function this way, which is, it's a nice way to do it, because now you have like something where you're controlling with minimal recreating of stuff. You can change what the time steps are, what the final time is, those kind of things. And then at the bottom here, we would say return T and T. A little confusing having like T and T, but here I have time and there I have temperature. There's no limit on how many characters variables can take, so really I could call this like time and then that one temp, but time and temp. And now for this one, because I have these default values here, I can say Euler temps of n, And I'm going to say t and t is like this. And dt is not defined, but it is defined. Oh, I see. And we'll do this. So I have to define my own dt, t bracket 1 minus t bracket 0. So before I get, this is the way to correct this. So and as I'm looking at this, like, how do I know that that is the way to correct it? Sometimes fixing errors is more helpful than just seeing code run perfectly. So here, as you're reading Python errors, the best way to do it is start from the bottom. So the very last thing that it says is that dt is not defined. And when I come back up to the spot where it's using dt, it's in this line where I'm trying to plot something. So for some reason, when I'm looping through n, there's no dt defined, even though it was defined inside of Euler temps. And the reason for that is that anything that gets defined inside of a function is a temporary variable. It's going to create that variable and then immediately flush it out of the namespace. So it's not an accessible value. So this dt does not exist outside of the function. So I'm calling that function, but it's never actually giving me that dt value. One way to fix that is I could say that dt is an output, and then I would have to have another output this way. But rather than do that, I'm just saying, like, okay, the time step is this t1 minus t0. And now I've got this solution that way. And it would help if I put a legend in there. So I can actually look at the labels that I'm spending the time to put in. And now I've got this demonstration of convergence, that as I keep decreasing that time step, it keeps getting closer to that analytical part. Some things that I noticed is that if you forgot this dt, it's still going to give you curves, but the curves will look kind of weird. Like in this case, it does look like it's converging, like they're getting closer together, but it's not converging to this analytical solution. Like it just looks like I'm making different, like all of these have different time constants, which is not supposed to be the case. It should be that the smaller the time step, you get closer and closer to this, this black line. And the reason for that is that it's as if I was plugging in a *1, which means that my time steps are 1 hour time steps. So from here to here, it's assuming that it was moving in this 1 hour step, as if the temperature decreased for that entire hour, even though I'm saying only half an hour had passed. Yeah, so I noticed that. Another thing was I saw here, if I plug in t of infinity into this equation, so in this step part B, and let me grab this equation. I know I use some fancy like LaTeX equations here, but I can say t as t goes to infinity equals ta plus t0 minus ta e to the negative k like that. Oh, and I can change that cell. I can change cell from like code to markdown with Y and M, but I can make like new markdown cells that way. And let's so this is going to be T0 minus TA, and e to the k times infinity is 1. Or sorry, it is 0. My bad. If I could do some math. So if you want to use this equation to say that as time goes to infinity, this is that, then there should be like some kind of evidence of like, all right, this is the T infinity equation. Just thinking about like what I noticed as I was looking at the projects and like how to help kind of explain the work that you're doing, because I saw some people say like part B T infinity equals TA. It's like, well, where did that come from? How do we know? Like, and another way to do this, kind of the numerical way of doing this, is that I can just plug in, like I have this function that I know is converged, right? Like if my time steps are small enough, then I know that it's the right answer. Or I could plug in values in here. Like I have all these different ways of, there. So I'll take this. So if I look at 30 hours, it looks like it's 65. If I look at 300 hours, it still looks like it's 65. And I could say, here, let's grab this, plug it up here, call it T analytical is that. If I look at the last value, so -1 is going to index the last value in that time, it's exactly 65, 65.0. And if I want to double check, I could say print that, and it's still going to say 65, 1.10f. And depending on how long I let this thing settle, because really it's an exponential curve, but at some point it's going to be 65, yeah, 65 Fahrenheit. Temp at T equals. And again, just different ways of trying to like show, and different like problem solving methods for doing this kind of like computational work versus this is the very like math, like there is one exact solution kind of problem. Like, okay, T goes to infinity, I can plug that into this mathematical thing, versus saying like, all right, well, I've got this function, infinite time is basically like, because my time constant is kind of half an hour, if it's anything more than 30 or 300 hours, then basically the time's infinite. There's no change, nothing's happening after 50 or 100 hours that way. Yeah, different ways of showing same kind of thing. What else? Was there anything else that I noticed? Part C. Oh, and the last thing was figuring out like what was the time of death. So here, and again, there's more than one way to do this. I saw one example of, Here, let's take this, cut it, and paste it down here. The one thing that I could do is say, like, all right, I have my function. And if I look a tenth of an hour backwards, or let's do like 10 minutes before 11 a.m., I get 86. If I do 20 minutes, now I'm looking at 88. 50 minutes, 93. So I could try to get closer and closer to 98.6 just through a guess and check method. But one person noticed that if you look up from scipy.optimize import fsolve, and we'll look at what the heck is fsolve, like what are you talking about? Fsolve takes a function and an initial guess, and the output is the root of the function. So it's going to tell me when this function equals 0. So this one is not going to help me because this doesn't actually go to 0. It goes to 65. But what I can do is define a new function that does go to 0 when it's the right temperature. So I could say minus 98.6. So now this is going to be 93.9 minus 98.6, or negative 4 degrees. If it's 0, then this function is equal to 98.6. So now I could use this thing called fsolve and say fsolve of my func, give it some initial guess of like negative 0.5, and I get this value of negative 1.17 hours. Cool. When was this? What time was that? So I know it's time 0 is 11 a.m. So 11 minus 1 point, well, let's just t pass. So oh, I see. 11 plus t pass. So we have a negative 1.17, so I'll add that. 9.83 hours. We don't really think about time. At least I don't think about time in terms of like how many tenths or hundredths of an hour have passed. So now I know print time of death was 9 colon and so 0.83 times 60, and I'll put an AM in there, 949.8, and really we'll do like a colon 1.0f like that. So time of death was 9:50 a.m. where I'm taking this value, and if I want I can plug in more, right? 83271 4, kind of round, but still within a minute it was 9:50 a.m. And this all depends on that value of k. So if you're getting a different time, that's okay, but remember how you defined k and what process you used to get there. Like were you using forward difference, backward difference, averaging the two? They're all a little bit off, all a little bit all good approximations for this kind of thing. Cool. So that was project 1. Thanks for all of your hard work on this. Right now, hopefully you're working through homework 2. So we're jumping right into analyzing data now. So here we have some different approaches to like computational thinking, where now we're looking at like what are the statistics and how do we gain insights based on like big sets of data. So we'll load in some data sets from here. We'll load up homework 2. We're loading in data sets from this transistor data from, I didn't mean to do that, taken from this Wikipedia page, and it's probably time to update it, right? Since it's now it's 5 years later. But now, yeah. Anyway, so we'll load that in. This head command. That's all I'm looking for you to do. The reason I'm showing you this is called a bash command. So breaking this down, this little exclamation point takes you out of Python and back into the whatever's running in the background. So in this case, we're running Linux. So it gets you into a bash interpreter. Same thing would happen in Mac, because that one's also like Linux, Unix. But it gives you a way of looking at what does the raw data look like when I'm trying to load this in. When I look at it, there are the first row are some labels, and then immediately after that, every row is same kind of format, but just different data. And the things that I care about as I'm trying to deal with this is like, what is the MOS transistor count? What's the date of introduction? And then who made that transistor? So as we're trying, or who made this semiconductor transistor thing? But it's a useful little tool to like let you see it. Another way of doing it would be like just open and go one folder up, which is where that data folder was, and then come down to this transistor data. And now I can actually look at, and I could edit this if I wanted to get rid of these question marks or anything. But being able to like look at the data as you're trying to get it into Python and actually deal with it, it's pretty helpful. I think it's pretty helpful. Otherwise, it's as you're trying to troubleshoot, like, why is this not working? How come this doesn't do what I want it to? Usually it has something to do with like, well, you thought there was a column named date, but it's actually a column named date of introduction. Little things like that. And then we'll also look at like this beers filled. The goal here is creating this same, so here's like the first version of the bubble plot, and here's the next version. So we're going, in this case, we took every row that had a missing value and deleted it. And then in the homework, what I'm asking you to do is take every missing value and fill it with a 0. So all of those IBU values that were missing, where they weren't measured for some reason, they'll all get filled in with a 0. So it'll change where these bubbles end up. And you could even add these, if you add these titles, then it's a little easier to compare this plot to your homework plot, because then you can see like, where did American Pale Ale fall? And because we're adding some zeros, it's probably going to drop it down like to the average value, maybe 40 or 30. Like all these values kind of drop a little bit, but we'll also have a bunch of zeros, where right now nothing has a 0 IBU. Yeah. And then, yeah, so we'll do more data processing, and then even look at the random generation. And I saw people saying like import random. Random is great if you just need like 1 or 2 random values, but a better way So instead of using import random, is saying from numpy.random import default RNG. RNG equals default RNG. A lot of times I give it a seed so that if you're trying to reproduce what I'm working on, you end up with the same random numbers as me. So they're not random, they're pseudo-random. They look random, but they are reproducible. So that's what this seed is giving you, is that you can create reproducible random numbers. And then I could say rng dot rand, and let's look at 10 random numbers. Oh, rng dot random. There we go. 10 random numbers there. So instead of like importing that random and generating one at a time, this lets you say like, okay, let me get 10 random numbers. Or I could even say like rand int. I think it's rand int, right? No, integers. And now I have to look at question mark. So I would give it a low, a high, and a size. So I'll say 0, 10, if I could write, and let's do 6. We'll say we're rolling the dice. And let's see, low and high. One above the largest sign. So this is, so if I want to go from 1 to 6, I need to say 1, 7, because this high is saying that it's 1 above the largest. And now I get 1, 5, 4, 3, 3. So it's as if I rolled the dice 10 times, and these are the 10 numbers that I got. Yeah. And we can do all sorts of other things. But this RNG, this default RNG, it's a better way of generating these pseudo random numbers rather than like importing random. This lets you like work with bigger sets of numbers and start doing more statistics and that kind of thing. Cool. I'm looking forward to seeing your module 2 work, and keep up the great work. All right, see you next time.